Doing equilibrium for weak bases is exactly the same as doing equilibrium for weak acids. So all the stuff you did with 16.6, you're doing the exact same thing for 16.7. There's not a bit of difference. Weak bases, the major weak base to know is, of course, ammonia. And then other weak bases that are going to pop up are going to be any conjugate base to a weak acid, because we saw that for a weak acid, its conjugate base is always weak. The base dissociation constant is abbreviated Kb, just like the acid dissociation constant was Ka. And if you have a really, really low value for Kb, then that means you have a really weak base because it's not making a lot of product. It is not dissociating very much, so it is weak. Just like with weak acids, when you have low Kas, that means that they are weak acids. Another type of weak base that you may see is an amine. An amine is something that we saw in our organic chemistry chapter. Remember the basic structure of an amine. It has some sort of organic group attached to it, and at the end of it, it has a nitrogen and a couple of hydrogens. And that nitrogen has a lone pair. And the reason why this is a base is because the lone pair on the nitrogen can attract a hydrogen ion. And so since it can be a proton acceptor, that makes it a base. So if you see compounds that end in amine, like methylamine or something like that, then know that those are also weak bases. And then we already said that the conjugate base of a weak acid is always going to be a weak base. That's what this means by anions of weak acids. That means conjugate base of a weak acid. So for the weak acid hydrofluoric acid, F negative is the conjugate base of that weak acid, and since it's a conjugate base of a weak acid, that makes it a weak base. Now, like I said, you do these types of problems exactly the same as you do the Ka problem. So you start with your balanced chemical equation, you start with your equilibrium expression, you got a value for X, you plug it into the equilibrium expression. It's the same kind of stuff. So why don't you go ahead and try it yourself first, and then pause it and try it, and then unpause it and check and see if you got the right answer. Okay, here's our equation. And here's my equilibrium expression. Notice that I did not put water in my equilibrium expression. That's because water is a pure liquid, so it should not be in my equilibrium expression. Now I'm going to do my ice table. Okay, so here's my ice table, and notice that I did not include water. Again, water is not part of my equilibrium, so I do not have to have it. And now I'm going to plug this into my equilibrium expression. Here's my equilibrium expression. Notice I did 0.15 minus x and assumed that was about equal to 0.15. That's because my Kb is small, so I can do that. And when I solve for x, I get 1.6 times 10 to the negative third, which is equal to my concentration of my hydroxide ion. Now there's a magical relationship between Ka and Kb that will help you solve a lot of problems. This is a real important thing to know. If you multiply the value of Ka of a particular acid times the value of Kb for its conjugate base, then you're always going to get the same thing. You're going to get Kw, which we remember from before is 1 times 10 to the negative 14th. All right, this will work for any acid and its conjugate base, or it will work for any base and its conjugate acid. It's a wonderful equation. We need to make sure that we know it. And then another good relationship to know is pKa plus pKb. What's a pKa and a pKb? Well, it's just like a pH. A pH is the negative log of the hydrogen concentration. So a pKa is the negative log of the Ka. So if you add the negative log of the Ka and the negative log of the Kb, then what you get is the negative log of Kw, which is equal to 14. So these two equations together allow us to find Ka if we have Kb, allows us to find Kb if we have Ka, and allows us to solve a lot of different things. And so these are both real important equations for you to memorize. So if I was going to take a look at this problem right here. Calculate the calculate the acid dissociation constant for the ammonium ion. What is the ammonium ion? Well, it is the conjugate acid of ammonia. And if I take a look back at my previous problem, I know the Kb of NH3 is 1.8 times 10 to the negative fifth. And so that means that I can easily find the Ka value of NH4 plus because I know the relationship between a base's Kb and its conjugate acids Ka. So I've got the Kb of NH3, I can plug it in this equation, and I can solve for Ka. And that will allow us to find the Ka. Well, except that should be 10, not 11.